Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but still want to be its friend. I'm your host, Dr. Moiya McTier. I'm an astrophysicist, a folklorist, and a good friend to the universe. I'm recording from my office here at Pale Blue Podiversity, and I'm expecting a special guest, another faculty in the College of Multitude here at the Podiversity. Dr. Sam Jones is going to be joining me. She's a biomedical scientist who, like me, left the research side of academia to be a writer and a podcaster. She hosts and produces Tiny Matters, a science podcast from the American Chemical Society, and we're going to have a chat about the tiniest things out in space. Sam should be here any minute. Sam, come on in.
Hi, thank you so much for having me. Very happy to be here at Pale Blue Podiversity. It's beautiful, really lovely.
I do love the campus. You know, in the mornings when I'm walking to the office, I just love all the trees. Did you know there's a waterfall just outside my window?
Oh, delightful. I'll have to check that out after the recording.
Yeah, it's frozen now, but in the spring it's going to thaw. It's going to be great.
I love it.
Would you like any tea? I want everyone to be very cozy when they come into my office.
You know, I'm feeling pretty hydrated, but thank you.
Excellent. Okay. Well, then let's jump right into things. How are you doing? Is there anything else you would want people to know about you?
Yeah, I'm the exec producer and co-host of Tiny Matters, which is a science podcast, which is part of Multitude as well, which is a blast. And yeah, like Dr. McTier said, my background, I guess, originally was in research. So I did my PhD in biomedical science, love science, didn't totally despise being at the bench, but I'm really, but I'm really, really happy to be able to communicate science to a much broader audience. So this is very fun. It's fun for me to be here today. It's very fun for me to be in the SciComm universe on a day-to-day. So it's all great.
Yeah, we're SciComm colleagues.
Yes.
It's really nice.
Yeah, it is.
Well, I want to get to know all of my colleagues better here at the Podiversity and outside of it. So I have this little questionnaire that just kind of gives me insight into who you are as a person. Would you mind answering some of my questions?
Sure. Ask away.
All right. I'm excited. First up, when you think about the universe and your relationship to it, how does that make you feel?
Based on my deep breath, you might expect me to say a little overwhelmed. Like, I think the universe is, of course, massive, right? And so I think it's something that for me is always very hard to grasp, which is why I love this podcast, right? Because you're making it something that is maybe feels less massive in a way because you can understand bits of it.
Trying.
So, yeah, I think like overwhelming is probably how I feel about it, even though I think it's cool, but overwhelming.
Yeah. I mean, we get overwhelmed by cool things here on Earth all the time.
Yes.
I mean, have you ever been starstruck by a celebrity? Of course. We get it. That's really nice. What do you think it would take for you to be less overwhelmed by the universe?
So I think what's overwhelming to me a little bit is that I'm someone who generally feels best when they're in control. And the universe is everything's out of my control, but the universe feels especially out of my control. But I think understanding bits of it better and why things are the way they are, the things we know, the things we don't know, just being able to even talk about it makes me feel better.
Same.
Yeah.
Not about the universe, but about things that make me feel uneasy, because the universe has always just been a big comfort. But I think talking about it, it's like a type of therapy, like exposure therapy, right?
Yeah. Yeah, absolutely.
Okay, second question gets a little bit less deep. Hopefully you won't have to heave any heavy sighs. But do you have a favorite unit of measurement?
Ooh, that's a great question. My gosh. I think like meters, but like more specifically millimeters, because I think a lot of really cute stuff is measured in millimeters. Like I worked just out of undergrad, I worked as a research technician at a lab in Kansas City at the Stowers Institute for Medical Research. It was a stem cell lab focused on regeneration. And the model organism we used was this non-parasitic flatworm called a planaria. And they're these like really cute, they kind of look like anime characters because they have these big like eye spots. They're so cute. But anyway, I was always thinking about those in millimeters because you're like, oh, it's 8 millimeters, so it's probably going to split pretty soon, like that kind of thing.
Mm-hmm.
So I think that's, but then there's just cute, like little baby flasks that are just like millimeter lines, or rather they're milliliter lines in those, but I guess the millis.
Yeah.
But when I think about a cute thing, I think about an animal and you're measuring it in millimeters.
That's adorable. Wait, that's such a great answer, actually. Also, the fact that you said cute thing and then you went to this like tiny little bug creature.
I swear it's so cute. If you look up a planaria, they're really cute. They're really cute. Definitely. After you're listening, like go look it up. It's so good.
Yeah. Okay. I fully believe you. I'll post a picture.
Specifically the species Schmidtea mediterranea, because not all of them are as cute, but that's the one that's very cute.
And it's what type of bug is it?
So it's a flatworm. And it's a aquatic flatworm. You could find them actually in a ton of places. It's a non-parasitic flatworm. They're usually, anywhere from like 3 to 10 millimeters in size. They're just cute. They kind of just like wiggle around, and they can split into, I think it's like one worm can split into dozens of pieces, and each one becomes its own one worm. Like they're amazing. Like they are masters of regeneration.
Oh, I love that. Yeah. We should learn something from that. I'm sure we are trying to learn something from that.
Yeah. There's a lot of people trying to learn something from that.
Great. Do you feel like your sun zodiac sign fits your personality?
So I'm so bad at this. So my sun zodiac sign is like the standard one, right? Because I know there's like moon something. I don't know anything.
There are lots of them, but just like the main one that most people talk about.
Yeah. So I would be a Pisces. So my birthday is March 4th. And so I'm a Pisces. It's a water sign. I was a swimmer. I competed through college. Nice. I love being in the water. There's certain other elements of like, I think Pisces are generally thought of as being like pretty nice, but also like pretty disciplined and a little intense, like type A, sometimes what I read. And I think I'm a pretty nice person. I am also type A. so that checks out. Yeah. I don't know so much about it though. So yeah, maybe I'm more or less Pisces than I think I am.
I mean, it's all a mix. Yeah. I know very little about Pisces.
Okay.
So
okay.
I'm just going to take your word for it.
Yeah. Yeah. I'm like, some astrologist is going to be like, excuse me, she was wrong.
Really, the purpose of this question is to see what salient parts of your personality you pick out.
Yeah. Nice, but type A.
Cool. That seems like a really good fit for multitude.
Yeah, actually. I think you're right.
If you could see any other part of the electromagnetic spectrum outside of the optical, which region would you choose?
Oh, maybe UV. I feel like there's a lot of animals that can see some really weird stuff because of UV.
Oh, yeah,
and so
like
I kind of like, I feel like, do snakes have that capability? I'm not sure, but I feel like it'd be cool to see the world through the eyes of a snake. I don't know. Actually, snakes, maybe it's like infrared. I might have this wrong, but yeah, no, not UV. They would be like infrared, but whatever. It doesn't matter. I chose UV. I still am curious and I want to see. I'd be outside. I'd be like, wow, I'm getting so much sun damage right now. Like,
I know. Yeah, you would see all of it. When you looked up into space, it would be a lot brighter,
right?
In some parts, like you would see
like blinding in some parts. I feel like,
yeah, exactly. Like if you look towards the center of the galaxy or something, then that would be pretty bright to you.
Yeah, I would need either some special glasses or like my eyes would have to have an adaptation that would allow me to already see UV.
Right. Although you might also have to be outside of the atmosphere because our atmosphere does block a lot of UV light.
It's true. Yeah, I wouldn't see as much coming through for sure.
Mm-hmm. But if we sent you to the ISS,
oh man,
you'd be our best telescope ever. Awesome. Okay, let's send you to the ISS. Let's give you your UV vision and send you to the ISS. When you are launching off of the surface of Earth, what song would you want to hear playing in the background?
Oh my gosh. You know what's so funny and kind of embarrassing is that the song that immediately came to mind was like that like Savage Garden song from like 20 years ago that's like something about a ticket to the moon and back or something, which I don't actually want to be my launch song, but that just came to mind. Oh my gosh. I think like that would make me a little bit anxious. Like I think being in space would be very cool, but it's nothing that I actually currently desire to do because I am a little, it does like freak me out a little bit. Like I'm very happy on Earth. I mean, generally speaking, not always, but generally pretty happy here on this planet. I think I need something like really upbeat. Like I need something from the Temptations or something.
Ooh.
Yeah, like I think something upbeat from the Temptations would be my launch song.
What is it? The Buttercup song? Is that what it?
Yeah, Build Me Up Buttercup.
Build Me Up Buttercup.
But then there's also this song that's like Get Ready, because like I think it's called Get Ready, but it's like Get Ready because here I come. It's a really fun one.
Oh yeah.
Yeah, I think that's my launch song.
Excellent choice. You're announcing to space, hey, everyone out there, get ready.
Yeah, exactly.
I'm coming for you.
Yeah,
that's good. Nice. I feel like I know you a little bit better now.
Good. You're like, and we can still do the interview, so that this is a good sign.
Yeah, and I'm not kicking you out of my office.
Yeah. Still allowed at the university, at the podiversity.
You have an open welcome here.
Appreciate
we'll give you
it.
a badge and everything.
Thank you.
Of course. I hear you have some questions about small things in space. And by I hear, I mean I asked you to come up with some questions about small things in space. So what are you especially curious about?
Yeah, so I'm very excited. I have a few questions for you. I'm going to start with, what is the smallest planet that we found in the universe? And sorry, this is kind of like a part A and B, but the B is, and do scientists think that there are ones that could be smaller?
Ooh, great questions. I love a multi-part question, actually, as long as you don't make fun of me for forgetting the second part halfway through.
No, I'll always bring it back up. Don't worry.
Okay, good. Yeah, so the smallest planet that we've found is in our galaxy. We actually haven't found any planets outside of our galaxy, but we expect that the populations of planets should be fairly consistent throughout the universe, at least at the current time. But the smallest one we've found is called Kepler 37b. So it's the first planet in the Kepler 37 system, where A is like the star of the system. Okay. And the star is very similar to our sun. It's a sun-like star. It's about 210 light years away in the constellation Lyra. Are you familiar with that constellation?
I am not.
Yeah, it's not one of the big ones. It's not like in the ecliptic or anything, but it's a northern hemisphere constellation around like 35 to 40 degrees north in latitude. Okay. It was discovered in 2013, which is about halfway between Kepler's start and Kepler's end, and it orbits really close to its star. It orbits every 13 days.
Whoa. Yeah. So is it like this? I'm like, how hot is it? It must be very hot.
Very hot. Scientists estimate that on the surface, it's about 800 degrees Fahrenheit.
Ooh.
So, yeah, very, very close. It's way closer than Mercury is to our sun. And it's smaller than Mercury. It's about 1/3 the size of Earth. So it's between the size of our moon and the size of Mercury, but still bigger than Pluto.
Okay. Got it.
Yeah.
Got it.
Which I think is a hint to your next question, the part 2. Because it's kind of hard to estimate what the lower limit absolutely should be. Right. If you have a planet that's made of really dense material, then it can be small but quite massive.
Right. Yeah.
Mm-hmm. But Pluto is probably a good proxy for a lower limit. It's about 1/5 the size of Earth, and at least with the composition that it has, which is rocky stuff that's common in our solar system, it was not massive enough to become spherical, which is what you need to do to become a planet.
Right. Yeah, that was the thing I was kind of thinking about, where I'm like, could you get a teeny tiny planet like the size of a house or something? But I think there's no way that could have enough mass to actually be a planet. Yeah,
exactly. It wouldn't meet its gravity makes it spherical rule.
Okay. Got it. Oh, that's really cool. I love that.
Yeah. And we haven't found a smaller one since. It's been over a decade, so Kepler 37b still holds the tiniest crown.
Oh. Very cool. So, Tiny Matters is a general science podcast, but we are created by the American Chemical Society, produced by Multitude. So I do think about the like elements and, like thinking about things on a tiny, tiny, tiny level a lot when I'm coming up with episodes. And so I was wondering how the vacuum of space affects how and if different chemical elements can combine.
Ooh, good question. What does vacuum mean in like a more chemical context? I'm wondering if it means the same to astronomers.
That's actually a great question, and I haven't thought about that. So I will say also that my PhD was not in chemistry, it was in biomedical
Right.
science. So when I was thinking of a vacuum, it was more essentially like sucking as much air out of something as possible, and that's it.
No, that helps, because the vacuum definition that astronomers use, at least, is that the pressure in a space is zero. So that's why we have this association between vacuums and like sucking air out of a space, because you need suction here on Earth to make the pressure in a little container go to zero, because you're sucking all the air out. So out in space, when we say vacuum, there's not like that sucking action.
Right.
But that's just because in most of space, which is really, really empty, you don't have molecules around. So you just like don't have any molecules exerting pressure on the space. So that's why we call it a vacuum. And because there are no molecules in the air in most of the empty parts of space, then you're not going to have things combining because they're just not there.
Gotcha.
But in between all of the really empty stuff, you do have areas of high density. Obviously, we have planets and stars, but there are like big clouds of gas where interesting things happen.
Right.
And I'm wondering if you have a sense for how dense our atmosphere is compared to those gas clouds out in space.
Oh my gosh.
If you had to guess.
I don't know, because now I'm thinking about the vacuum of space and how that affects the density.
Right. So, well, like there are parts of space that are more vacuumy. And then there are parts of space that aren't. So in the parts of space that aren't.
In one of those gas clouds, I feel like that has got to be, I think it's more dense
than our atmosphere.
Yeah.
All right. Here, I'm about to blow your mind.
Yeah.
Because that is what people think, right? When you see those gassy clouds, when you see the nebulae in the beautiful Hubble pictures, they look really dense.
Right.
Right? And when in Star Trek or something, they're passing through a gas cloud, like they're traveling through something that looks very dense, like a cloud of fog here on Earth.
Yeah.
It's so much less dense, orders of magnitude. So here on Earth, in a standard cubic centimeter of atmosphere, you can expect the number is 30 quintillion molecules in that 1 cubic centimeter. That's 3 and then 19 zeros.
Okay.
Out in space, the big nebulae where things happen, like stars form there. There have been recent supernova explosions in those nebulae spaces sometimes. They have a maximum molecular count of like 10,000 molecules per cubic centimeter.
Wow. I never would have guessed that. It throws you off because, it's like what you're seeing looks like a bit of a sandstorm or like fog, like you said. And so you think, it's got to be more dense, but no.
But no.
Wow, that's so cool.
Yeah, that is why if you're sitting with an astronomer or with an astrophysics person and you're watching one of those sci-fi films where they're flying through space and they feel called to point out inaccuracies, that's probably one thing that they will talk about.
Oh, neat.
Yeah, so to answer your question directly, yes, the vacuum parts of space make it very difficult for elements to combine and create new ones. And that's why you only see the creation of elements in these dense spaces.
Yeah. Amazing. I'm going to remember this. It's very cool.
Yay.
Okay. So correct me if I'm wrong on this, but I learned that comets are just icy bodies of frozen gases. I guess we can't get away from gases in space. So comets are icy bodies of frozen gases, rocks, and dust that were left over after our sun formed. I have a few questions about this. So I'll start with the first question. Can you find comets all over the place?
Yeah, you should be able to. We haven't detected any elsewhere, but that's just because they're so small.
Right.
And all of the methods we have for detecting things in other stellar systems only work for things bigger than that. They barely work for small planets.
Okay.
So we do expect them to be everywhere because they form through a process that we expect to be universal.
Okay. Fascinating. And are they always moving? Because I think when you think of a comet, you think of something like streaking across space or, like are comets always moving?
Ooh, yeah, they are. So comets form very similar to how planets form.
Okay.
When you have a very young star, not all of the material in the gas cloud where the star was born will go into the star. There's going to be a disk of debris swirling around it. And the planets form by tiny little dust grains accreting onto each other like a snowball falling down a mountain.
Okay.
And smaller things can also form through that process.
Okay.
You also get some comets and asteroids that form through like planets and moons breaking apart. But the difference between a comet and an asteroid is that the comets are icy. So they come from further out in the solar system beyond what astronomers call snow lines. So every type of compound, water, methane, anything, it's going to have a snow line, which is the distance from the star where it's cold enough for that particular substance to freeze. So after snow lines, you get, instead of dust grains, you have ice grains. And ice is stickier than dust, so it's easier for things to build up through the accretion model in the outer parts of the solar system. And because these comets form in the same way as planets, they're going to move in the same way as planets. So they are also orbiting the sun, and they are going around all the time.
Oh, that's so interesting. And so when I think about like an icy thing orbiting the sun, to me that says it's not going to last forever because the sun's so hot. But I don't know, they can be really far out, so who knows. But I'm wondering, like, after around 4.6 billion years, right? Like if these were all left over after the sun formed, like why haven't they all disintegrated into tiny pieces?
Ooh, yeah. Many of them have.
Okay.
We've actually observed it. Back in 2020, the Hubble Space Telescope observed a comet breaking apart. In real time, which was really cool. The comet was called Atlas, or Comet 2019 Y4.
Okay.
And
do they know why it broke apart?
That is still kind of an area of study. Your intuition is really good here. They are icy things that go around the sun, and they do lose material when they do that. The iconic image of a comet is that stone in the front, and then there's a tail following it.
Right.
And that tail is all of the material that are being evaporated off by the heat of the sun. But most of these comets spend a lot of their orbit much further away from the sun than here at Earth's orbit. So they aren't being evaporated that strongly most of the time. And some of them they're big, right? It's really hard to melt through miles of ice.
Right.
Yeah.
Which is like hard to imagine, like in a moving thing in the sky. But yeah.
One of the cool areas of research into comets is looking at the different comet compositions, because when you can kind of tell where in the solar system a comet formed based on what elements are in it, because you can tell which snow line it was closest to. And when we study the comets that are still here versus the ones that have disintegrated, that we've like observed disintegrating, we're just trying to figure out what are the compositional differences, because maybe the ones that are still around are made of substances that are just stickier or more resistant to heat damage or something.
Yeah. Huh. We need some of that to help with our glacier disappearing problem. I don't know, whatever it is.
Exactly. Yes. See, this is just one instance of astronomy research being really useful here on Earth.
Oh, totally. Yeah. No, that's really cool.
Yeah.
Thank you.
Questions.
Thanks. They were fun to come up with.
I'm glad, because I don't know if you spend much time thinking about really, really big scale things.
I don't. And so this was actually really fun to push myself to think that way.
Awesome.
Yeah.
I rarely think about really, really small scale things. So this is also kind of me pushing outside my comfort zone.
Nice.
Hi, friends. Dr. Moiya here. Sam found the drawer that I keep full of the Eat Me cakes and the Drink Me potions that I got from Lewis Carroll's estate, so she's going outside on my office deck to try them, and I figured I would use these few minutes to share a few messages with you. The first message is a huge thank you to all of my patrons who support the show financially. As an independent podcaster, it would be really hard to make this show without your support, so thank you. And I want to welcome my latest pre-main sequence star, Allison Maidlow. Welcome and thank you, Allison. I also want to give a special huge thank you and shout out to my Sun-like stars, Scott Reynolds, Augustin, Tom T, Nicole Bartlett, and Ashley Shambo. I just really want to thank you all for not having too much magnetic activity going on. I think I speak for maybe the entire flora and fauna population of the Earth when I say that. So good job. If you want to join this awesome group of people, hear your name on the show, make it onto my Patreon star chart, and get research notes for almost every episode for just $5 a month, you can do that by joining at patreon.com/palebluepod. Hotter tiers, like my Sun-like stars, get access to Pale Blue Pod at night, where I read bedtime stories, by which I mean my PhD dissertation, in what I hope is a calm and soothing voice. And even brighter tiers, like Blue Giant stars, get to see full videos of episode recordings. You can also sign up for an annual membership where you end up getting a 13% discount across an entire year. That's 1 percentage point for each constellation on the ecliptic. Of course, I appreciate you just for listening to Pale Blue Pod, but any additional support you can give would be greatly appreciated, so thank you in advance. The next message is a podcast recommendation. It's another show in the Multitude Collective, and it's called Join the Party. This is an actual play podcast with tangible worlds, genre-pushing storytelling, and collaborators who make each other and the listeners laugh each week. GM is Eric, and he's joined by emphatic players Amanda, Brandon, and Julia, who all welcome everyone to the table, from longtime TTRPG players to folks who have never touched a role-playing game before in their lives. You can hop into their current campaign, which is the drama and excitement of a superhero high school. It's told through the game Masks, which I've never played before, but don't worry, they teach you everything that you need to know about the game to enjoy the story. But you could also hop into their completed stories. Campaign 3 was a pirate story set in a world of plant and bug folk. The campaign was a Monster of the Week game set in a weird summer camp. The second campaign was a modern superhero game, and there's definitely some connection between that one and campaign 4. And their first campaign was for fans of a classic high fantasy story. So really, there's something for everyone over at Join the Party. So what are you waiting for? Pull up a chair and join the party by searching for the pod in your favorite podcast app or by going to jointhepartypod.com. Sam is back, and it seems like she is her regular size. She doesn't seem any bigger or smaller. Very impressive. You know, she is a scientist after all. She can really balance out the effects of those size-changing potions. But you know, I've done this before. Her depth perception is going to be off for a little while. That's okay. You don't need to know how far away things are to talk about how big and small things are in space. Actually, you do. But for the purposes of this conversation, I promise she's fine. I wanted to talk about the smallest things that, or some of the smallest things that exist in the universe and where they came from. Elements and like atoms. I think people don't necessarily always really consciously think about the fact that these atoms formed in space.
Right.
So I wanted to talk about it. And there's no better episode to talk about it than in the Tiny Things X Big Things episode.
Yes, it's true.
It's true. So a lot of what I'm going to say here comes from Jennifer Johnson, Dr. Jennifer Johnson, who a few years ago put out one of my favorite graphics, actually. It's the periodic table, but instead of like the element name and its atomic number, it has the name and then a picture or a color coding that tells you where and how in space that element mostly forms.
Oh, I feel like I have seen this. I don't know it well, but I've definitely seen this because I remember seeing it being like, that is so clever and I love it. Yeah.
I know. If I were like a scientific poster on the wall type of person, I would
have that
absolutely hang that baby up. It would be that. and the radio frequency allocation chart.
Oh, that's a fun one, too.
I feel like a really good get to know your fellow nerd type of question is, what's your favorite scientific graphic?
Yes.
So she made that graphic and also studies the different origins of elements. So like an astrochemistry type of research.
Yeah.
And as an astronomer, going through your typical training, you usually hear about the Big Bang and the elements that it created.
Right.
And you probably learn about the elements that are created in stars, but that's about it. We don't really learn the rest of it in your fundamental astronomy classes. You have to specialize in astrochemistry to get there. So some of this I knew, some of this I really didn't, and that was exciting.
No, that's cool.
Yeah. So what if I say the terms Big Bang nucleosynthesis? Does that mean anything to you?
It means a lot in that I think we definitely wouldn't be here without it. So my understanding of what that is on a very general level is just the creation of atomic nuclei. So and you need atomic nuclei to have atoms, and you need atoms for everything. So that's my understanding. And it kind of ends there.
Yeah, pretty perfect. Yep. Big Bang nucleosynthesis is specifically talking about the very first nuclei and the very first elements that formed after the Big Bang. So even still, most of the universe is hydrogen. Like 75% of the universe and like the molecules in it are hydrogen atoms. And then about 25% is helium, which is just a great cosmic joke, isn't it? That we are experiencing a shortage of one of the second most abundant element in the universe.
Right. Yeah. And I do forget that. But then when you think about it, it's kind of, it doesn't make sense, but it makes sense.
Right. Like a sad clown needs to present this information, but then the sad clown couldn't have a balloon.
Right. Sorry, no balloons today, kids.
Right. That's why it's sad.
Yeah.
So mostly hydrogen and then 25% helium with tiny trace amounts of lithium and deuterium, which some people call heavy hydrogen.
Oh, yes.
It's like, okay, yeah, so you've heard of it.
Yeah, I think deuterium, I think, is important for, I'm thinking about nuclear reactors, and you need heavy, I don't know. But essentially, for fission reactions, you need some heavy elements too. Mm-hmm. Yeah.
Do they use the heavy water, like the deuterium water in the nuclear reactors?
Yeah,
is that what it is?
That's my understanding. And apologies to nuclear physicists and chemists if I got that wrong. But I do know that it does play a role in nuclear reactors, or at least it did in nuclear reactors of the past. I don't know how things have changed over the last 30-ish years.
Very interesting. I didn't know they were used in nuclear stuff, but that makes sense because it's fission, it's fusion related.
Yeah.
So yeah, you use the stuff. But deuterium is called heavy hydrogen because it is very similar to a neutral hydrogen atom, which has one proton and one electron, except the deuterium atom also has a neutron in there. So it has the extra mass of a neutron added, which is I don't think it's fair to call the deuterium heavy at that point.
Right.
It's just one more neutron.
Yeah, it's very judgy.
But okay. It is. So you get the atomic nuclei first, where it's just the protons and neutrons working together. Mm-hmm. The electron, it's too hot for the electrons to bind very early on in the universe. So after a few minutes, you get atomic nuclei, and then it takes 300,000 years for things to cool down long enough for the electrons to bond, and you get neutral atoms.
Wow.
Yeah, wild. So most of those atoms, hydrogen, helium, a little bit of lithium, and then about 100 million years after the Big Bang, you start getting the first stars forming. And those first stars, because they're mostly hydrogen and helium, they burn quick. They burn hot and fast, and just like the stars of today, they are producing heavier elements in their cores. So over time, each new generation of stars that form have heavier elements inside them before they start making even heavier elements. So it's this nice cyclical process.
Yeah. Okay, that's interesting.
Mm-hmm. Yeah, it's a beautiful feedback loop. When I'm trying to get people to understand like how connected space is over time. That's one of the things that I mention.
Yeah.
It's like the different populations of stars. So stars will do nuclear fusion in their cores, and they'll start by fusing hydrogen into helium. And then as they fuse most of the hydrogen in their cores, they develop this shell of helium around it. And so then they start to fuse helium into heavier elements. And that process works up to iron.
Okay.
And then as the stars continue along their life cycles, they do diverge. The high mass stars do one thing and the low mass stars do another. So the high mass stars will eventually, do you know what happens to them at the end of their lives?
Do they become white dwarfs?
That's the lower mass stars.
Oh, I flipped it. Okay, they explode?
Yes. Okay, yeah, so you got both right. High mass stars explode as supernovae, and that energy produces a lot of heavier elements up to rubidium. And then the low mass stars can actually produce even heavier elements, probably because they last longer and they do some fun things too, like eventually go into the red giant phase. They shed their outer layers and then they become a white dwarf, which, if there's another star around, can become a different type of supernova, which produces heavier elements than the massive star supernova.
Wow. Okay.
Yeah.
That's
Stars are complicated, and there are all these processes in them. When I was in grad school, I remember hearing about like different fusion mechanisms for different stars in different mass groups. I remember hearing about like R processes, which are rapid processes, and then the slow processes, and it's just like it's so complicated.
Yeah.
Which is why people go to school for many, many years to study these things. I was never really like a stars person, but there's a lot there.
Yeah. No, it sounds like it.
Yes. So those low mass stars, once they go supernova, they can make really heavy elements like up into the bottom row of the periodic table.
Oh, wow.
But you're not going to get things like the heavy metals like silver and gold and like platinum without really energetic collisions out in space.
Okay.
Did you hear about the like neutron star mergers that we detected with gravitational waves?
I did not.
Ooh, okay. Maybe a fun episode for Tiny Matters. If you can find a way to get them to send you out to like CERN or something or LIGO or something, I'd be so jumping at that opportunity. But yeah, so back in 2017, I think it was, we detected two neutron stars merging, and we detected it in gravitational waves, and then we also detected it in light. We called this multi-messenger astronomy, where we could see it in both. And what we saw was that this neutron star merger produced a shit ton of gold, like a Jupiter's worth of gold. And I think we had known for a long time that those types of collisions should produce these heavier elements, but we like observed it. We got empirical evidence back in 2017. So those colliding neutron stars, they make the heaviest stable elements. So silver and gold, all the way up to bismuth, which I didn't realize was that high up on the periodic table. But it's the thing in Pepto-Bismol that makes your tongue black.
Oh, weird.
Yeah.
Huh.
And it's produced in colliding neutron stars.
Yeah, that is wild. And so, like, how long would it be? I guess you'd have to have like a meteorite or something like for it to, like for that specifically to make its way to Earth, right?
Ooh.
Or like how I'm thinking about all these elements in space, and of course, like we live on a planet that is in space, that was created in space. Like if you dig into the ground, there's a lot of elements in there, right? But like thinking about these ones that like have just been made.
Yes.
Like how long until they would maybe reach Earth?
Probably never.
Yeah, okay.
Things in space do move, but they tend to move as a group. We call it like co-moving. So all of the stars orbit, but if a star explodes up ahead of us, it's going to keep moving and so are we. So it will stay up ahead of us.
Right.
All of the elements that we have here now were formed in explosions and collisions that happened kind of in this same area of space before the sun formed. Things can gather, they can collect through gravity, but that's only the really, really massive things that will make that much of a difference.
Yeah. Interesting.
Yeah. So when we get any new elements here on Earth, it's from asteroids and meteorites that come from other places in our same solar system.
Yeah. Okay.
Yeah. Except for Oumuamua, which we think, based on its velocity, came from outside the solar system.
Oh,
but still nearby.
Okay.
Yeah. There are a whole bunch of elements that are radioactive. So there are some elements that form through other processes, but they themselves are radioactive, so they will decay into other things.
Right.
And then there are some elements that, as far as we know, or at least according to this graph, they form from the radioactive decay of other radioactive elements.
Okay.
Mm-hmm. Does that sound right?
Yeah. So radioactive elements forming from the decay of other radioactive elements. Yeah. Mm-hmm.
Yes. Yeah. And then they will also decay.
Yeah.
So they're not as stable as gold or carbon or something.
Right. Yeah. No, that makes sense.
Yeah. So like radon is radioactive, and it mostly forms through other radioactive elements, just like falling apart until it becomes radon.
Right. I mean, that's part of with nuclear reactors, you have the formation of new radioactive elements from radioactive elements because you have this fission or fusion that's going on.
Yeah, exactly.
Yeah.
And then there are so many elements that we can only find made in labs here on Earth, the human-made or the synthetic elements. There are 24 of them.
That's actually kind of more than I thought for some reason. Huh.
Okay, so you are not super familiar with the names of these 24 synthetic elements, you would say?
I would say I am not.
Okay, excellent. That's good. I made a little game type thing, and I was worried that you would know all of them, and then the game would be ruined.
No. You are safe.
Okay, fantastic. So all of these synthetic elements are named after the people or places who were involved in their discovery, and I think that's hilarious. So I have this little game where I'm going to give you two different synthetic element names.
Okay.
And between the two of them, you have to say which is the real synthetic element, except sometimes it's both and sometimes it's none.
Oh my goodness. Okay. All right.
So is it none, both, or A or B?
Okay.
So there are 5 questions. The first is Copernicium versus Keplerium. I guess it could also be Copernicium.
Okay.
Which is real?
Yeah. I want to say A is real.
Okay. Is that instinct, or are you remembering something?
I don't think I'm remembering anything. But Keplerium feels like, okay, we just talked about Kepler and but it just feels too vague, maybe?
Oh, interesting.
I don't know. So I'm going to go with A.
Copernicus is super specific. Yeah, you're right. It is A.
Oh.
I'm just salty because I love Johannes Kepler and I want him to have an element named after him.
I mean, that would be cool. That would be cool. Yeah.
But Copernicium is named after Nicholas Copernicus. And when you look at all of the other people that these elements are named after, there are some astronomers, but mostly physicists. It's mostly physicists and chemists. And to my knowledge, Copernicus was not a chemist. So I think that someone who named this element just really admired the Copernican revolution.
Okay.
Yeah. Yeah. I know nothing about what these elements do or are or anything. I'm just going off of names. Okay, next one. Which one, both or neither? Texium versus tennessine.
Okay, I think tennessine is real. But I don't think
said that
Texium
immediately.
is. Yeah, I don't know why, but it just stuck in my mind. And I'm like, maybe I've seen that. Maybe I'm just kidding myself. I don't know. But I would say
No,
B
you're
is
right.
real. Okay. Yeah. That one I've definitely heard.
Yeah, you're crushing it. I was like, Tennessee. I did not expect Tennessee to be one of these names. And I figured that Texas would get mad that Tennessee had a distinction it did not.
Yeah, for sure. I'm actually surprised there aren't more states that have
Yeah,
it.
me too.
Yeah.
There's one for California, so there's Californium, but there's also Berkeleyum.
That one
which is
I know.
for Berkeley.
I know Berkeleyum because it was discovered at Berkeley, like at Berkeley Labs, I believe. Yeah.
Yeah. And then there's like a Livermoreium or something for Livermore Labs, and a lot of them are named after the labs or the cities that they were discovered in.
Yeah. Interesting.
Just be a little bit more original, please.
I know.
Please. Okay, so this next one, Franklinium versus Chaldrine.
Oh, whoa. Chaldrine's kind of like weird and pretty. Like it sort of sounds like it could be a name, but also an STI. So I'm not sure. I want to say A is correct.
Is this instinct? Are you remembering?
No, that was instinct. I think it just sounded more like it would be an element name to me for some reason. Like the other one it didn't have like the same, like I feel like not that the names are like harsh, but there was something about the second one that just felt like too mellow to be an element name.
Yeah, this is too pretty and or too much like an STD.
Yeah, exactly.
So
exactly.
So you're right, Chaldrine is not an element. But neither is Franklinium.
Oh, my goodness.
I named Franklinium after Rosalind Franklin, who was a pioneering scientist. Yeah. She was foundational in DNA research. She did X-ray research, crystallography stuff, and was not given the recognition that she deserved. And Chaldrine, I named after Uma Chowdhury, who is a chemist who does a lot with like ceramics.
Oh, that's cool. Well, so sorry that was my take on that name. No disrespect.
No, of course, no disrespect. But I wanted to add these to bring attention to the fact that there are not these synthetic elements named after women.
Yeah, that's not shocking.
No, not at all. There is curium, but even that is for both Marie
and her husband.
Pierre. Yeah. So there is no synthetic element that is named just for a woman in science, which is ridiculous. So now we have Franklinium and Chaldrine.
Yes, perfect.
I like to imagine that Chaldrine is very useful in the kilning process.
Oh, that would be
for ceramics.
Yeah, that would be perfect.
And Franklinium is what do you think Franklinium would be?
Franklinium to me, maybe it would be some element that like speeds up the DNA replication process or something like that.
Ooh, I like it. Or maybe it slows it down.
Or slows it down because we don't really want to speed it up. It controls it. Yeah, there you go.
Okay, well, hats off to Franklinium and Chaldrine. And next, we have Seaborgium versus Flerovium.
Like, Seaborgium is fun, but it doesn't feel like it would be an element to me. What was the second one?
Flerovium.
I'm going to say that's real.
That is real. Okay. And so is Seaborgium.
Really?
Yeah, it's named after a scientist, like some Dr. Seaborg.
Something Seaborg? Okay.
Which is a baller name.
Yeah.
Seaborgium. Great. And then finally, Dublinium versus Moscovium.
Oh, geez. I feel like Moscovium is real. I don't remember ever seeing Dublinium. I feel like Moscovium could be real for Moscow, but I might be totally wrong.
Moscovium is real.
Okay. But is the other one real too?
Dublinium is not real.
Okay.
I just really like Ireland.
No, I like Dublinium sounds really cool, but I was like, I don't think I've seen that anywhere. But yeah, Moscovium. Okay.
I didn't write down the real element's name, but I think it's dubinium. I think I just added the L, or maybe it's dubnium.
Dubnium.
So I just added an Li.
Yeah, it kind of sounds like Dublinium anyway.
Basically the same. I mean, I think we should just give it to Ireland.
Yeah. Let's just give it to them.
Well, you did a great job. You know way more about the synthetic elements than I think you do. Yeah,
it's possible.
Excellent. Do you have any further thoughts or curiosities about tiny things out in space?
Oh my gosh. Well, there's so many. And I think you're right. I think it is really cool because I think when we think about space, we only think about big stuff a lot of times. Like when I think about the stuff I do, I often just think about small stuff. And it's really fun to think about the small stuff in the big stuff or the big things that come from the small stuff. So Yeah, I really want to go see that video of a comet that you mentioned. I think like that is on my list to do today because it sounds cool.
Yeah. I think they have like snapshots of it, but there's this really cool picture where you can see that it is broken up into several pieces.
Wow, that's fascinating. Yeah, no, I think I don't know. I mean, I guess my only question would be for you, like, is there, as you were thinking about these questions that I asked, like, was there a tiny thing that really stood out to you where you felt like, oh my gosh, that's kind of mind-blowing and I didn't know that?
Ooh. No, I think all of these, for the questions that you asked, I knew. There are not very many small things out in space, but there are surprisingly small things out in space that are like absolutely large, but something like a stellar mass black hole.
Okay.
Have you heard of these?
No, but it sounds scary and awesome.
They're not that scary, but people talk a lot about the supermassive black holes.
Right.
But there's just one. There's just one in every galaxy on average. We have 10 million stellar mass black holes in our Milky Way galaxy alone.
Whoa.
That are a few to maybe 10 times the mass of our sun. So they're really tiny and they barely have any sort of influence, but they're out there.
Wow.
And I think people would be shocked by that.
Yeah, that's a lot.
Yeah. By how there are a lot of like small dwarf galaxies, we call them, these little satellite galaxies. There are like 40 of them around the Milky Way. Yeah.
Huh.
There are surprisingly small things in space sometimes.
Yeah. Amazing. Well, I just learned a lot.
Yay. I'm so glad. I learned a lot too. And I learned a lot about you, which was really nice.
Yeah. I'm so glad that we could do this.
Yeah.
So glad I could take a trip to this university.
Thank you. But yeah, like I said, you have your ID. We'll get you a parking pass. We don't even make people validate their parking here because what does that even mean?
I know. Because this is a classy institution.
You're right. We're classy and we care.
Yes.
We've got both. So I care about you. I care about listeners finding your work online. So could you brag about yourself, what you're doing, and where people can find you?
Yeah, totally. So you can find Tiny Matters on any listening platform. So wherever you listen to podcasts, go check out Tiny Matters, subscribe, rate us, review us. That would be amazing. Also, you can find me and the other stuff that I do at sjoneswriting.com. I do a bunch of random freelance stuff as well. And so a bunch of more like writing for outlets like Washington Post and stuff. And so I get to really dabble in a variety of things. But my primary thing is definitely Tiny Matters. So go listen. I think you'll enjoy it. There's an episode for everyone. It's really very diverse in terms of the topic matter. So go check it out.
It is. It seems like a really fun job where one week you are researching something that has nothing to do with what you were doing last week.
Yeah, it is. It's really fun. I think what I learned about myself in graduate school is that like I get really excited about a lot of things and I get bored really easily. And so it's perfect for me to have an episode where I go so hard, I go down a rabbit hole, I learn as much as I can in the time that I have. We do an episode and then I'm like on to the next thing. So, we'll do an episode on like frostbite one week. The next week we're talking about like the evolution of plants. The week after that, we're talking about some deadly infectious disease. Like we're just going for it. So yeah, we have some great stuff in store for the rest of the year for sure.
Oh, I can't wait to hear it. And listeners, the link to Tiny Matters and to Sam's links, they're down in the episode description. So check those out. Awesome. Well, I have had a lovely time discussing things big and small with you, Sam.
Me too.
But I have to go teach a class. So no matter what the biggest thing in space you've ever seen is, you are still a part of space, a small but important part of space. Pale Blue Pod is hosted by me, Dr. Moiya McTier, a.k.a. the universe's bestie. I created the show with original co-host Corinne Caputo, a comedienne extraordinaire, and help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen, and our audio editing is handled by the incomparable Misha Stanton. I am Go Astro Mo everywhere online, and you can stay in touch with the show and the universe by following Pale Blue Pod on Instagram or checking out our website, palebluepod.com. We are a member of Multitude, an independent podcast collective and production studio. So if you like Pale Blue Pod, you will love the other shows that live at multitude.productions. And if you want a shout out on the show and research notes for every episode, you can join our community over at patreon.com/palebluepod for just about $1 per episode. Thank you so much for listening to Pale Blue Pod. I'll be back next week. Bye.